All right, in this video, we will talk about classification versus regression. So the idea of classification is closely related to choosing from a given number of alternatives. And regression essentially means that you would assign a score from a continuous range, from a continuous space. So let's review what we were talking about in the last video. We have visually identified the idea of the task as a function, in this case, the decision function. We have in our left-hand side our input space. We have in our right-hand side the output space with the possible responses that our model can generate, can give as outputs. We have our learning objective that is essentially to learn the optimal set of values for our parameters. And we also have the hyperparameters that are parameters that are actually set by ourselves, by the person or the persons that are setting up the model. And the learning essentially means that you would be navigating in that parameter space to find a model that gives hopefully the best metric given some performance. So we also mentioned the definition, and the definition with the alternative definition as well, focused on the idea of optimization. So I really like the idea of boiling down the learning problem as an optimization objective, as an optimization algorithm. And also there's the idea of the performance metric, and the use of the training data as that source of information that would be used by the model to learn the best parameters. So the training of the model or the evolution of the model essentially means that you would be optimizing over the parameters and also over the hyperparameters in different ways, as we have mentioned before. So now let's focus on the definition on classification tasks. So we are focusing for the most part in this course on supervised learning. So supervised learning means that we will be using data data that has labels, that has been manually tagged or labeled in a way. So this means that we can perform some tasks that could be using some sort of metrics that would essentially try to align the outputs of the model to the outputs that you have in the training data. So in the case of the classification task, we are talking about selecting from a finite set of alternatives. So let's visit one more time this diagram. Imagine that you have your inputs, again, left-hand side, and you have a number of different outputs. So each of the outputs would be a class or a type or a category, and that category would be one out of so many categories that lives in the C finite set. And that would be the main thing that characterizes our classification task. You are choosing a class or a category, or in some cases even more than one, out of a finite number of possible responses. So a few examples to classification tasks. So for instance, if you are heading to the control deli and you want to choose a sandwich to have lunch out of the menu. So an example of a classification task would be to choose which sandwich would be the best sandwich given some input that you specify, or maybe to determine which series from Netflix should be shown in the first page in a specific day, in a specific time, for a specific person. Or maybe another example would be which of the three classification function outputs to select. So in this case, imagine that you have not one model, but multiple models, and you want to actually choose which model, which function would be the best one. So that's, again, one more example of choosing out of so many options out of a finite set C. So that also is an example of a classification task. So the simplest form of classification is what we refer to as binary classification, because we only have two possible alternatives. So as you see in the slide, you have examples of that. And that's a very traditional setting where you only have either 1 or 0, or 1 or 1 minus 1, or go or stop, or yes or no, or true or false, always like one thing or another. A generalization of this idea is when you go to more than two possible classes, possible outputs. So imagine that you are, for instance, choosing a number, a digit. So a single number, you can only have the digit being 0 or 1 or 2 or all the way to 9. Or maybe you are choosing out of the letters of the alphabet, or maybe choosing out of a possible set of colors. So that's also one example of that idea. One thing that can happen as well is that the cardinality of my set might actually change with time, or even the dynamics of the model itself follows that idea. So for instance, this is very typical to be seen on a turn-based game. So imagine that you have like a board game, like tic-tac-toe, and depending on where and on which stage you are in the game, obviously you would not have the same possibilities every time that one of the locations, one of the cells have been previously picked. So you cannot actually pick the same cell again. So that's one example of a simple turn-based game where the possible outputs change with time. So that there's this idea of a dynamic class set. So another example that we have here is choosing from given an image that is an image of a digit, a handwritten digit, a number. We want to identify which that digit would be. So that's again one classification, one example of a classification task. And then we would be choosing out of 10 possible outputs, essentially, right? The standard way in which we do that is by just picking one digit out of those 10 possible digits. So you're only picking one at a time. So that would be the idea of the standard classification. But actually, there's different ways in which we can do that as well. And one way in which we can do that is one different way in which we can do that is with the multi-label classification, where you would actually pick not one output out of the possible n, let's call it n, number of classes that you have in your output set, but you might pick up one or more possible alternatives. So in this case, the multi-label setting means that you don't have a fixed number of categories that will be chosen at a time. It might be one, it might be two, it might be all the way to all the ones that you have available. So these are a few examples of that. So imagine in your right-hand side here, you see this image of a sort of a car, but that is actually also a mouse. You can see from the scrolling thing on top of it, right? You see there's an USB thumb drive thing there. So these can be classified as a mouse, but also as a car, but also based on perhaps the colors that are part of that. So possible labels that we could actually assign to that image in this example would be blue or car or mouse. So you actually have three outcomes that are chosen out of a number of possible outcomes that we have. In the second example here on the bottom, we have one more time a digit, a handwritten digit. And in this case, you have something that resembles the number 7, but perhaps this can be understood as a 1 as well. So it's not completely clear if we have there a 7 or a 1. And then depending on the setting, obviously, and your requirements, it might be interesting to actually choose all the possible numbers that might be recognized from that image. So in this case, you could perhaps be selecting both 1 and 7 as the classes, as the outputs for for that given input. So again, the main characteristic that we would see on a classification is that you have only so many possible alternatives, right? So you don't have an infinite number of alternatives, so you don't have a continuous space. Instead, you have a discrete or a enumerable space where you can only pick out of that many choices for your output, for your classes. This does not mean that the number of classes is necessarily a small number. So in some cases, actually, you have a very large number of possible classes. That's actually quite typical to see in natural language processing. So in most natural language tasks, you would see the number of outputs that are possible as let's say the next words that would be appearing, given that you have seen the beginning of a sentence. So essentially, you have all the different terms that appear in a vocabulary. So we're talking about in terms of the English, we're talking about possibly tens of thousands of different terms that could appear, and each of those words could be one of the classes that we have. So in this case, we have a significant large number of different classes. You can also have classes that are ordinal. So the class set being ordinal means that there's some relationship in the outputs that you have. So the example that we have used before, the digits, you have the 0, 1, 2, 3 all the way to 9. So there's a relationship on those outputs, because you know that 2 represents a number that is larger than 1, and 1 represents a number that is larger than 0, and then so on. Same idea with the sequence of the letters of the alphabet. Same idea with some form of grading, like low, medium, and high. So these would also be examples of ordinal classes. And finally, you also have the nominal classes. So you only have classes that do not have any underlying ordering. So examples of that would be colors. So there's no really any sense of sequence of order when you have the colors, or maybe just names that you are applying to a given object, or possible paths from A to B. So now let's move to our second category of supervised learning, and that is the regression. The regression tasks, as we have briefly mentioned, involves assigning a score. So now you have a value that is going to be predicted, that is going to be given as output out of a continuous range. You don't have no more the idea of the discrete possible values as we have seen on the classification task, but now you have this idea of a continuous range, and the prediction would essentially be given a value out of that range. So this usually means that we would be given an output out of a range. So this range can be even infinite. So you can think of the real line if you are giving out a number as output that goes from minus infinity to positive infinity. But you can also have a more well-contained smaller range. Like, for instance, you can have the range limited to only be within -1 and 1. So it's a continuous and infinite range, but it is limited in the range itself. So the maximum and the minimum value now are set. So that's also very common to be seen. So in terms of the output space, we see a lot of possible ranges, as I have previously mentioned. So typical ranges that you would see, limited ranges would be 0 to 1 or -1 to 1. And this is sometimes actually imposed by some operation that we perform. Usually the last step, you can apply, for instance, a hypertangent or a sigmoid, and that would essentially limit the possible outputs that you would get, the range that you would get. So here, another thing that I want to mention is that sometimes you might actually be predicting not one output, but more than one output. And one good example of that is when you are when you are training a model or defining a model to generate representations, we usually refer to these representations as embeddings. So embeddings are essentially just a vector, a number of numbers. So you have, if you have a, let's say, a 10 position vector, you have 10 stacked numbers. Each of those numbers would be could be generated by one separate regression function. So in this case, you would be not generating one single value, but many numbers at a time, every time that you generate. So in this example here, we have embeddings, two-dimensional embeddings, because we only have two axes here, that represents word embeddings. So word embeddings are this idea of these vectors that are associated with terms, with words. So if you see here, you would see words that are somehow related by you, and the way that we show that here is by using the same color in those dots. So you see that the points in that two-dimensional space that we have here, when they are colored the same way, so they belong to roughly the same family. So then you see that there's a sort of a relationship depending on how close or how distant one term is from another. So that's also one very popular example of a regression task. This is also representing the same idea. So here, imagine that you are trying to predict the next word given a sentence. So we are trying to predict, let's say, the word dog from my input. My regression might be generating a few numbers, and those numbers would be essentially forming a vector, an embedding. So you don't have one single output being generated, but you actually have many outputs being generated, and that's what's represented in that right-hand side diagram here. So how do we relate those two things? How do we relate regression and classification? Regression is kind of given. So the way that we would define most models would be actually via a regression function, but we also want to perform classification. So how do we perform classification? By taking advantage of a mathematical formulation that actually is a regression. So if you think about the same kind of idea that we had before, we have an input, you have a regressor. That regressor is going to generate a given score, a given number. If we have three possible outputs here, what we are going to do is essentially generate one regressor for each of those possible classes that I have. So if my output space has three possible classes, I would essentially be training or generating three regression models. And then I use some criteria to actually identify, if I want to identify only one class out of that three possible classes that I have, I'm going to go with the one that gives me the highest score. So because I have these three different functions, these functions will be giving me different values. In this example here, as you see, you have the values 0.25 for the first class, 0.75 for the second class, and then 0.1 for the third class. Which of those are which of those classes are the one that gives me the highest score? That would be the second class, right? The one that we have identified here, coloring it as black. So this one in the middle is the one that would have the highest score, and that's how I would know. That's how my classifier would identify which class would be the output of that overall classifier. So essentially, I stacked up multiple regression functions, and then I just used a function to pick up the function associated with the highest scoring of those regression functions. So the selector here is really just picking up the highest score one, nothing more than that. So there's no parameter learning in that step. So in the traditional, in the canonical classifier, we don't really learn anything about the classifier itself, because we already know that we are just picking up the one that gives out the highest of the scores that are being generated. And that concludes our video on classification tasks and regression tasks, and how these two compare against each other, and how especially we can use the idea of multiple regressions to combine into a single classifier. And then based on regression functions, we can essentially generate a model of a classifier. I will see you in the next video. Bye-bye.